and welcome to the first in the series of TVS colloquiums that we are hosting. Today's speaker is Nina Hernitschek. She is in Vanderbilt University, and today she'll talk about machine learning for classification strategies of astronomical sources. Before we begin, just a few very simple rules. So Nina's talk will be about 40 minutes, and afterwards we'll have more than enough time for questions and discussion. So please wait with your questions until the end. And Nina, the floor is yours.
Thank you very much. So I will talk today about how machine learning is a very helpful tool in classification of astronomical sources, for example, for LSST, but also for other big surveys. So what I do and why I'm here, I work intensively on machine learning for big astronomical surveys, such as LSST, but not only LSST. I will talk more about the surveys I'm working on right now later on in this talk. I'm currently a postdoctoral fellow at Vanderbilt University's Data Science Institute and the Vanderbilt Initiative for Data Intensive Astrophysics. So this picture here describes quite well what I'm doing. So I'm heavily involved in survey planning, in algorithms to work with the data we get from the surveys. So it's mostly machine learning for different purposes, such as correcting outliers in the data. Then, of course, more on the science and classification algorithms, and then, of course, doing science with the data we get from our machine learning tools, such as large catalogs that can be built by using classifiers. So what is the thing that's very challenging in a big surveys we have nowadays is, of course, the data handling. We have an increasing data volume and data rate in nowadays astronomical surveys. So in this picture, the blue bars show the data volume, whereas the red and orange one shows the data rate. And you see both is increasing a lot. And just comparing, for example, LSST with SDSS, the daily data rate is about half of the total data volume that we had from SDSS. From SDSS. So this is a huge challenge in how to process the data. We have so much data that it's infeasible to look at all the data on our own. So we have to rely on machine learning tools that do the work for us to process the data, to do classification of astronomical sources, but also ways earlier in the step to do outlier correction and just help us to prepare the data. Big challenges are also that the huge amount of data often makes it absolutely infeasible to download all the data or even to download a reasonable amount of data. For SDSS, it has worked pretty well in many cases to download some tables, but for LSST, for example, it just will become infeasible to download a meaningful subset of the data. So we have to move our algorithms more to where the data is living. Also, it is sometimes infeasible to store all the data. This is something we had seen before in other parts of physics, for example, for accelerators. It was not possible to store all the data at experiments such as CERN and others. So algorithms have to decide what data is important, what data has a good signal to noise ratio, and focus on storing this data to forwarding it to us. Also, quite often we're doing additional observations. So doing follow-up observations, especially targeted at a subset of data. I can give one example I was working on. This was a spectroscopic survey. I was based on photometric observations where the targets were were found by using a machine learning algorithm that extracted our Lowry stars and Cepheids from the Pan stars survey. So this is very important to yeah, to get a good handle on the data. And especially the large scale follow up is extremely demanding. Now, with having a lot of data at hand, we can do such projects like, for example, extracting all stars of a certain type at a certain part on a sky, getting data from the light curves such as periods, phases, and then using this for follow up. This is a very cool thing, but it also makes it absolutely necessary to have reliable algorithms. And this is something where big data analytics and machine learning is an extremely helpful tool because it provides algorithms that are usually very fast and they're also capable with working with data that have a certain kind of imperfection. I can also talk more about this later on, but this as a short summary as an introduction in the topic. So what is very important, I think, is that big data is transforming how discoveries are made. It could also happen that big data allows us to find something in data that's already existing, but the data were not processed the right way right now. So this term big data, it comes up quite often, but what is it exactly? Okay, of course it must be something with a lot of data, but how do we define it? There are different definitions. So one of them is to say, okay, data sets whose size is beyond the ability of commonly used software tools. This is something that contains time variant aspect. So what today's big data is could be tomorrow's normal data, because this heavily depends on the um, computing facilities we have available. There's another definition, and I have to say I like this definition ways more. This is one from Lenny et al., saying data growth challenge is three-dimensional. So big data is data with at least one big dimension, but usually two or three dimensions are big. Volume, then the velocity associated with bandwidth, the response speed we need, and the variety, so the number and size of individual assets. This is something that's typically targeted with a large survey like LSST. We have a lot of data. We're getting in the data very fast, and we have a huge number of astrophysical objects that are seen by that survey, which makes it very important to have algorithms that can deal with a lot of different data, with huge of a variety of data, especially as the first steps in the processing pipeline. The user cases in this way are also shifting. So it becomes more important to find the right data, because something like LSST is producing a lot of data, and we won't lack cadence or number of observations in a light curve, but we have to find the correct light curves, the correct objects that we need for doing our science. And this is something where Statistical and machine learning tools can very, very good help us, and they step in at helping us with classifying objects, with classifying objects not only in a way to finding something that's matching a known pattern, but also helping us with what we call anomalies. So discovering something new, discovering objects that maybe with a worse cadence might look like something that we know, but when we can take a look with a more finely resolved light curve, then we can see it's something different. For example, in the case of all Larry stars, looking at different ways how effects with showing a period and phase modulation can take place. Not only seeing it's an Euleric star or it's modulated, but how it's exactly modulated. And another point is here also, we not longer have only individual measurements available like we had it decades before from the very small surveys, but we have so many data that we can deal with statistics, clusterings, patterns. For example, to come back on phase and period modulation in variable stars, we have more examples. We have more cases, for example, to show some modulation is going on in a certain way, and we can find more examples to finally do statistics. For example, finding if certain patterns in light curves occur more to stars that are maybe older or younger or have a higher or lower metallicity. This is something that we can only do when we have a lot of data, but it also means data needs to be processed highly automatized, and the analysis is much more exploratory than predefined and scripted. Means we can explore our data space. We can see what might be in there without having something predefined. This is something that is very different from earlier approaches, and is also something that is only possible when having a huge amount of data available. Just to give a few examples, what can be done also from further surveys. So for example, for PENSAS 1 3Pi, I was working heavily on getting a classification pipeline set up. And this enabled us, for example, to filter out from about 10 to the 9 rather sparse light curves in the end, about 44,000 RB stars. And later, experiments with doing spectroscopy on them proved that we indeed got them right by more than 99% from super sparse light curves. And this is something that was only possible with machine learning. So to be honest, when I saw the data the first time, I had not thought it might be feasible to do anything at this level with the data. But machine learning tools can be so reliable that it was indeed possible to filter out those stars. Something else, what is also quite new, is doing transient science based on gravitational wave follow-up. This is something that's, for example, done now a lot with the ZTF survey, and also their machine learning helps a lot to quickly detect sources. Something else more on the side of cosmology is working with dark matter, dark energy through weak lensing, and this requires often to combine data from different surveys, to run a lot of models, to compare the data to models from lensing events, and then to do data-driven approaches, leading in the end to large catalogs, archives, and also something that is heavily driven now by modern analysis methods from the big data. One thing I mentioned a bit earlier was we're doing also statistical data analysis. And this is something that's only possible when we have a lot of data available. And it brings also in something in addition that is quite nice, that we can run models without having the bias of physical models. This sounds a bit strange, but I can show one good example here. So on the left side, you see the little cross is showing the points of a light curve. This is a light curve from a quasar. The line connecting the points is not fitted from a quasar model, but from a more general model that can be fit to nearly every variable source. It is called a multiband structure function. And the structure function is relying on 2 or 3 parameters. You see the MCMC sampling on the right side, and the algorithm is deciding what is the best matching combination of those 2 parameters, A and gamma. And later on, we could use, for example, a machine learning algorithm that learns which of the combinations from A and gamma is typically for quasars, for Cepheids, for Larry stars, for asteroids. And then this machine learning tool can help to filter out the objects to build a large catalog. But this was done without using a physical model of the behavior of a star or of an astronomical object at this point. This is something that's also super helpful in detecting new events. So when we're fitting physical models, then we're already have some pre-assumptions what we're looking for. We're looking for certain types, and then we might miss out the very interesting and new events that are going on. But with such methods, we can catch them, because then it shows up in a very, for example, as a very unusual combination of those parameters, but that is happening a few times, and then we can get a clue. Okay, there's a new it's a new type of object we're interested in. This is something that's I think a very very important thing to try to be as far as possible free from the bias of physical models, which of course doesn't mean that we simply should skip physical models. So we have very good physical models and we should use them, but I think we should not use them too early in the processing pipeline. The special requirements that we will get when we are using statistical data analysis and not relying on physical models, but also not having the physical models, is we have to find the right methods. So the statistical tools are really a vast amount what's available, and we have to find the correct thing that is working with the data we're using. Also, we have to take care that scientific inferences should not depend on the arbitrary choices in methodology and variable science scales. So it would be very bad for variability science if, for example, one non-physical model would give a result that would say these kind of objects or quasars, likely quasars, and another model would say by no way they are quasars. So then something is wrong, likely in the choice of methods that are just not working for the data. Also, we have correctly interpret the meaning of the statistical results with respect to our scientific goal. As I showed in the plot before, the output of this algorithm is a likely combination of A and gamma. We have to take care what to do with that, which can happen, for example, in a machine learning step that interprets the combination of the parameters, so the so-called parameter space for us. This term astrostatistics, I've mentioned it a few times, and to some people it might be quite new because statistics was and still is heavily influenced by human sciences. So traditional methods one would find, for example, in literature, software, are usually not applicable to astronomy or astrophysics. These are methods that are made more for human science. And yeah, when you look at the methods, you see quite often they assume each distribution is Gaussian or something like that, and it's not working with our data. But there are a lot of specifically tailored methods available that work very well with astrostatistics, with astronomy data, and it's called astrostatistics. And there are also nowadays a bunch of good books, a bunch of online tutorials, online courses, and there is a lot of things around. I would say since about 10 years ago. So, and this is also influenced by the upcoming big surveys like LSST, where we simply need the data. I would say the surveys we had during the last few years, it was something where it became more and more important to use those methods, but it was not absolutely required. But for LSST, for sure, those methods will be absolutely required to process a huge amount of data. What can be done with astrostatistics? There's a lot possible. For example, we can do something like galaxy clustering by using clustering algorithms. We can work on galaxy morphology also by using clustering algorithms, but we can also do a lot of other things like pre-classification by using what I had shown, structure functions and then a classifier. Or we can also do detection of very faint sources by running some statistics on a shape. So this is a very big field nowadays, and there are a lot of methods that were tested on specific use cases. what is often going on in these algorithms is that we're fitting some kind of a model, and this fitting a model could be very different. It could be something like a nonlinear regression process, like shown in the first plot, where we're just trying to meaningful connect points in a light curve. It could be something like density or shape estimation in the parameter space, or it could be, and then physical models again come in, doing parameter estimation of an assumed model. So what this plot is showing, we have a source that was already pre-classified as a very likely Larry star, and then we're using a template fit to find the correct phase and period of this object, even from a very sparse light curve. So here, a physical model was absolutely necessary because the data quality was not good enough to do an independent fit of the periodicity of the light curve. But we have only done this after we have run other steps in the processing pipeline that made it extremely sure that we are indeed dealing with a Larry star and not maybe a Cepheid or some other source that shows a periodic variability. What we have to take care of is fitting a model and then selecting the correct model. Criteria for a good model, yeah, of course, that it is good, but what does it mean is it should be a rather simple or the simplest possible model. It should enable a goodness of fit that we can define by a conformness fitted model to the data. It should be easily generalizable. This means that we can, for example, in the case of the structure function parameters, we can easily use it on different kind of objects. It is not too specific. And we should also take care that we're not underfitting. This means leaving out key variables where the data would be there to fit them, but we're just not doing this. But we also have to take care to not overfit, which would produce an unnecessarily complex model with extra variables, introducing something that is by far not in the data, but we have a model that assumes it would be there. For example, as I showed before, the plot of the phased light curve. We could run this model on nearly each light curve, and it would quite often show up there is some kind of periodicity, but it just isn't there. So we have to take care that we're not overfitting, because overfitting induces higher variability that is just not there, whereas underfitting could induce some kind of a bias. So a good model should balance the computing objectives of conformity to data and parsimony. So it's very important to really not only run those algorithms, but take care to do a very good model selection. What we're doing for automatic model selection is quite often using Bayesian statistical inference. For example, running a so-called Monte Carlo Markov chain optimizer is MCMC. And this is optimizing a function to get the best fitting parameters. It is a quite complex algorithm or set of algorithms, but it's nowadays existing in a lot of very good implementations that are available for programming languages like Python or C++. So we can rely in some cases on very good software libraries that can do a lot of the work, but we on our own, of course, always have to take care to select the correct model, because this is only a tool, and that's of course a tool that's not really thinking. Machine learning, as I said, thinking, yeah, machine learning is trying to mimic the thinking part in some way. It's a subfield of computer science that gives computers the ability to learn something without being explicitly programmed. What it is doing indeed is trying to uncover some hidden correlation patterns in the data through iterative learning by using some sample data. Here is one example showing the parameter space some different parameters obtained from light curves, where the light curves stem from quasars, from our Lyrae stars, and from a mixture of other astronomical sources. And in the plot, you see there is some discrimination between the sources based on their position in parameter space, but it's not that clear. You can say, of course, there is some part in a parameter space where, for example, the quasars or the Lyrae stars cluster, but it's not easy to just draw a line between them. But the machine learning tool can learn that, how to draw a line and how to separate between them. So what a machine learning tool indeed is doing is transforming a parameter space of measurements into the parameter space of astrophysical objects, because we're not so much interested that an object has a certain color or a certain period, but we're looking for example, a pulsating star or a supernova. And in addition, it can also be used to model a survey. This means to describe data quality, doing outlier correction. Then, of course, as I mentioned a lot, describing light curve characteristics for so-called features. And then in the end, we can use this to classify sources, to build catalogs, and using the catalogs to do science on them, also with using machine learning tools for finding, for example, substructure clumps over densities, as well in the physical space, but also in the parameter space. So clustering can be done in each kind of parameter space, and it simply means that members of the same cluster should be close in some sense. I guess this picture is giving a good example of what clustering means. And this is what we call also an unsupervised learning. So we're not giving an example on how a certain cluster looks like, but we let the algorithm choose on their own where are the clusters and how to find the clusters. One example for clustering methods is finding clusters in space, but also finding classes of objects. For example, gamma ray bursts. We can say, okay, there's at least 3 different classes of events for gamma ray bursts, and between them to separate. It's not easy if you're not knowing they're existing, but a clustering algorithm can on their own find, here is some different events going on, and they match to clusters the algorithm is defining. Classification, on the other hand, is relying heavily on predefined labels and on examples. So this is so-called supervised learning, where the algorithm is learning with labels. So it's presented with objects and a label that is saying this object is from a certain class, from a certain type, and then it's learning what is a typical Lyrae star, what is a typical supernova, how different can Cepheids be to still be considered as a Cepheid. This is what we're using, for example, for building catalogs of variable sources. Supervised classification is widely used, and it's super important because as we know in astronomy, we have a lot of classes. For example, spectral classes. We have variable stars and have a lot of different subclasses within them. We do a classification of AGN in different types and so on. We classify galaxies. So it's widely used. And it is, I would say, it is the largest use case we have for machine learning right now. What's going on internally in those algorithms is that a training set is used to enable the classifier to find certain characteristics associated with certain types in the training set, and then it is applied to a target set that we want to classify, and it's outputting probabilities. For example, how likely a certain source is from a certain class. What's happening internally is that the algorithm is building up decision trees, and it's usually building up different or a huge amount of decision trees to enable the code to do some kind of an ensemble method. So many of these decision trees are grown from subsets of training data or evaluated independently. And in the end, the method is voting for the most likely classification. This is very important because it might happen that when labeling the data for a training set, we occasionally have mislabeled something. This could always happen, but this kind of algorithm can correct for that. It can also correct for data that is not only wrongly labeled, but that have some kind of internal problems. For example, we have kind of an O'Leary light curve, but we have a very bad signal to noise ratio. The algorithm can find that this object is a correct object from this training set, but it has a rather high signal to noise ratio and might not be taken into account as a very important object in the classification process. So it's a typical object that could be occur, but it's not a typical object. So what I want to say as a summary on this is that this divide and conquer approach improves the classification performance a lot. So it's less sensitive to training set variances, like the thing with the bad signal to noise ratio. It's robust to outliers, like we have something mislabeled in a training set, and it can be run in parallel on huge computing clusters, which is extremely important when using this for something like LSST. What we should take care of is that we should never apply it as a black box. We have always to verify what our algorithms are doing. So for example, making use of a training set and then do something that's called a cross validation, where we held out a portion of the data, train on most of the training set and apply it to a small portion of the training set in turn to see how well it performs. And we also have some measures, I just show it here briefly, that enable us to validate how well the algorithms are running and to compare them. There are a lot of different implementations. I just show them here briefly, and you could look them up later on. They have some fancy names like support vector machines or recursive partitioning algorithms. They're available in many implementations. Also for languages like Python, C, and others. So there's a lot around. And now towards the end, I want to just give a brief overview of what I'm working on actually. So as I say, these are usually big astronomical surveys that need some machine learning tools to work with the data. And also means quite often then when having processed the data, for example, filter out objects to build a catalog, we're going a step back to do, for example, follow-up observations on targets we get from our own catalogs, and the process is running again and again. So we get more detailed data. We're again running some machine learning algorithms on them to investigate the data. One big survey I was heavily involved in is the PANSAS 1-3 Pi survey. This is an optical and near-infrared survey that's covering about 3/4 of the sky, non-simultaneously, and with only about 70 visits over 5.5 years. And this is a typical light curve, so it looks much different than this what we expect from LSST. It has a lot of challenges. You could imagine if you try to find a period of this library store, it looks nearly invisible. But it was possible with the right machine learning tools. And why we did this is that PanStars allows a view of the complete outer halo of our Milky Way, which is very interesting if one want to take a look at the old composition of the outer halo, especially the O'Leary stars. And the goal was to create a catalog of variable sources within the survey. While we're looking at variable sources, yes, that is because they are rather easily to detect. I showed the example light curve. The data was not that nice, but we were hoping that it was feasible to detect them from that data. And if you can detect them, the huge benefit is that they can be used for distance estimates. So can be used as important traces for the old halo substructure. Of course, we're also interested in other variable sources like Cepheids and quasars. And as we started right in the beginning in the survey, we also had to model the survey. So we needed tools for describing data quality, describing light curve characteristics, and then all the way down to classifying sources, and then finally finding substructure in our sources. It was super challenging because we had to process about 10 to the 9 of those rather spores and noisy light curves. So we had to skip some kind of algorithms that looked or that would give very nice results, but it were just not possible to use them on this kind of data. So as a first step, we had to find methods to do a meaningful feature extraction. So for this, we relied on the structure function I showed before, because it was very difficult to work with those non-simultaneous multiband data that were quite sparse, quite noisy. We had some foreground effects, and also very crucial, the time sampling of data can act as a window function. So it could hide true existing variability. So to cope this, we started out with non-periodic features like this multiband structure function that is shown in a bit more detail here. And here you see this method can discriminate between something like an Eulerian star and a quasar, because it can fit some characteristic time scale, as we call it. It's not a period, it's something very general. It's a time scale that shows on which typical time scale of variability occurs. For us, those two light curves on the left and on the right might look very similar, or at least we cannot say anything about them, but the algorithm is capable of doing this and clearly assigns a short time scale to the variable star and the long time scale to the quasar. These distance estimates that we used, that we got from the Eulerian stars, were then used to do a 3D map of measured magnitudes and the derived periods. And in the end, we were able to select sources. In a second step, by using template fitting. The template fitting, I also showed it briefly in the beginning. The template fitting is applied only to sources where we're pretty sure it's an Eulerian star. And then the template fitting helped us out a lot with getting the period right. This is computationally super expensive. And this was also the reason why we used it only as a second step. Because these algorithms run for a long time and they can find the correct period. We have tested it a lot, but they can be really only run on objects where we're pretty sure there is a matching template. To give an overview of what was done for the complete survey was that we started out with the light curves, did some outlier cleaning using the machine learning method, did feature extraction, and then did several classification steps subsequently with machine learning algorithms, and ending up with catalogs for Eulerian stars, for quasars, also for other sources. This is one example of how the map of Eulerian stars from the Pan-STAR survey looks like. So what's very obvious here is that in the middle and then going down, we can see the trailing and the leading arms of Sagittarius stream, completely mapped in Eulerian stars from the survey. This is where we started then doing our science to investigate the 3D structure of the Sagittarius stream. And here you see one example, a very clear view on the stream, the same way, completely traced in Eulerian stars from the survey and completely found by machine learning tools. We also did other things with the data, like fitting the Milky Way halo. This is one example for fitting a function to a complex data set. We also then used the data to run a follow-up survey. Our goal is to find co-moving groups and clusters in the Milky Way based on spectroscopic observations that are targeted on Eulerian stars found by this method. And the crucial thing in the follow-up survey was to get the timing correct, because the cause of the pulsation is that the cause of the pulsation in the light curve is that the star is showing some expansion and is shrinking again. And this is change in brightness is associated with also a change in velocity. So this velocity overlaps then with the velocity we want to really want to measure. So we have the intrinsic velocity, and we have also this center of gravity velocity. And we can only get it right if we have the correct timing, so we know in which phase of the pulsation cycle we are when we're doing our targeted observation with spectroscopy. So this is also one example why machine learning is very important to get the maximum out of the data. So if you imagine getting the period precisely correct from those light curves that um, show a really bad cadence, and this only worked with those tools. Here is this summary on how the calculation works, that we always have to take care of the systemic velocity of the star we want to measure, but also the photospheric velocity from the pulsation itself. And so we have to do the targeted observation at a specific point in the light curve. This was a large observing program we carried out during the last few years, and it's still continued. And the overall goal is to dynamically characterize the substructure in the outer galactic halo, with a lot of different sub-projects that are targeted on stellar streams, on likely pairs of outlier stars, and so on, with instruments like Keck telescope, Magellan telescope. And we've done a lot of observing nights. So this is one example, I would say, where it's very clear that machine learning has helped a lot to get the best out of the data. And a lot more is now possible from better sampled light curves, such as from TESS or LSST. These are light curves from TESS, and you see immediately they look a lot different than those from pan stars. We have a ways higher cadence, we have much nicer data, and so we can also apply very different methods. And there are also some very, very unconventional methods around to make best of noisy and sparse data. There's just something I found a few weeks ago, that people are trying to get stellar rotation periods from using the stellar spots, but they're applying a very novel algorithm that is running up to 10,000 times faster than algorithms used before, and it's very much more reliable. So this is also some improvement in totally different fields of astronomy that can be gained from using machine learning tools. My fun remarks on this are that the word classification now appears in about 1/3 of the astronomy papers since about 2012. It's widely used, but there are still a lot of heuristic methods around that very likely can and should be replaced by machine learning-based classification.
Okay, thank you, Nina.
Thank you.
This was very interesting. So we have time for questions now. I would like to ask you to please either raise your hand or type the question in the chat. And I see we already have a question from Ashley. So if you could unmute yourself and just go ahead. Oh, there was not a question.
Sorry, I was just applause. I pushed the applause button, not the question.
Okay.
Okay. So then there was a question from Federica in the chat, if you'd like to ask.
Hi, sure. Hi, Nina, nice to see you again. Thank you for the talk. So one thing that you mentioned is it would be really a problem if different models that we create were given different classifications. And I wanted to ask if it could also be an opportunity, right? So if we have models that provide different classification, if the classification is the goal, that might be a way for us to identify unusual objects. So is anybody using classifiers in aggregate to weed out anomalies?
For anomalies, I would more recommend using clustering methods that can can show up the anomalies without throwing them in some predefined labeled bucket like machine learning algorithms, like, for example, a random forest classifier, typical classification algorithms would do. So I think anomaly is a big goal also for LSST, because then we have so many data that we can also find those 1 in a million events. And we also have to take care that they don't end up misclassified in some classification structure, like from a supervised machine learning algorithm.
Okay, thank you. Sorry, no, continue.
And for this, I would always say that we should introduce physical models as late as possible in the step. Like I had shown for the pen stores, that we started out with a structure function and then put in the template fitting that is really relying on a physical model as late as possible in the step, when we were extremely sure that certain objects are, for example, our library stores, and the only thing that was left to find out is which subtype is an or A star or a C star, and what is the correct phase and period. So only then we introduce the physical model in the process.
Okay, thank you. There are any other questions that we have? Yes, Sumaya, please go ahead.
Hi, thank you so much for your interesting talk. I was just wondering, thinking of instead of just like using machine learning algorithms on one data set, if like we think about like using two data sets, is there like, is it possible to basically transfer information from one data set to another? And if you think it is, like what sort of features or what sort of algorithms would be more suitable for that purpose?
Okay, so quite often we indeed use more than one data set. So for example, the analysis on pen stores also relied on some data from the W map. Then also what is quite important is that we have to design algorithms in a way that we are able to transfer them to other surveys. So this is also possible, for example, to build a set of algorithms that is as much as independent as possible, to then transfer it to something else, like, for example, LSST or some of the other upcoming surveys. So what I find important is two things. The first is designing algorithms that are quite independent and transferable, but also when using them, taking care that they can be really used for the data we have at hand. So for something totally different, for eclipsing binaries, I was recently trying out some algorithms that were highly recommended by somebody, but in the end, it turned out that the data I have at hand is just not of a quality that is required for this algorithm. But whereas if I had a higher quality data, it would be a very good algorithm. So this is always some kind of a trade-off.
Thanks.
Any other questions? So while maybe people are still thinking, I have a question about this supervised learning. So I'm not that very much familiar with machine learning, but what if you have a some event that you know it exists, but it's very, very rare. So you only have, for example, one example light curve that you can use for your training set. So how do you deal with such rare objects?
In this case, we would rely on simulated data.
Mm-hmm.
We could simulate the event, and then what's very important, we have to sample it to the data rate we would get from the true survey, because it is a huge problem if we have simulated data that looks too good. Mm-hmm. And then algorithm would learn that the event would look precisely like that, and it would not find it in the true data. So we always have to mimic that the data is truly coming from that survey. So we have to take care of this in the simulation, and yeah, to downsample the data, to put the data in the correct waveband, something like that.
Okay, okay. Thank you. If there are any other questions, it's time to ask them now. So it doesn't look like anyone has another question. Okay, well, in that case, I think we can end today's colloquium here. Thank you all for attending. I hope it was interesting for you, and thank you, Nina, again for this very interesting talk. Bye.
Bye.